Alright, let's talk about simplifying radicals. What I'm going to do is I'm going to simplify the square root of 28. Now remember what the square root is. The square root is the inverse operation of squaring. So the square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5. These are nice and easy to do because these are called perfect squares. And I want you to think about what that means. This is the square root of 2 squared, because 4 is 2 squared. So the square root and the squared cancel each other out. This is the square root of 3 squared. Whoops, 3 squared, so they cancel each other out. This is the square root of 4 squared. So the square root and the square cancel each other out because they're inverse operations. When I have 28, the trick to this is it's not a perfect square, but it might have factors that are perfect squares. So we break down 28. Half of 28 is 14. Half of 14 is 7. So 28 is 2 times 2 times 7. That's called the prime factorization. And what do you notice about this problem? What do you notice about this problem? Two, and there's two 2's in there. So that's this. And now the rule is you could break up the square root since they're both factors like that. And this one is a perfect square. That's this. So the 2 and the squared cancel, and you get 2 on the outside and the square root of 7 on the inside. And that's how you simplify that problem. Let's try another one. Alright, let's try another one. So this is a little trickier because I've got a number on the outside. Now this is just a factor on the outside. So I'm going to rewrite this as 5 times the square root of, now let's break down 48. 48 I know is 2 times 24, and I know 24 is 2 times 12, and I know 12 is 2 times 6, and I know 6 is 2 times 3. So look at all my prime factors. So I've got 2 times 2 times 2 times 2 times 3, which can be rewritten as 2 squared. Let's erase this right here. I could have also written that instead as 2 squared times 2 squared times 3. Or I could have written it as 4 squared times 3. It doesn't matter how I write it, because no matter what I do, when I take out this right here is going to come out. This right here is going to come out of the square root sign. Because what's the square root of 2 squared? 2. So these are each going to come out, and I'm going to get 5 times 2 times 2. Those both came out. And what stayed in?
3.
A 3 stayed in. Now I can multiply these things out on the outside here, and what do I get? 20 square roots of 3, and that's my answer. Now, check something for me. If you would have instead, some people maybe you would have said, well, no, I would have just broken this right away. I would have broken that up into 16 times 3. And 16 is 4 times 4. And right there, do you have to break that down more? No, you could have just written 4 squared times 3. And now what happens? What comes out? That's going to come out as a 4 and a 3. It doesn't matter. You're still going to get the same answer, because there's your 4 times 5 would be 20. Doesn't matter how you break it. Once you recognize you have a perfect square factor inside of here, it breaks. I call it breaking jail. It breaks jail. It comes out. So if you see right away that, oh look, I know right away that that's 16 times 3, then great. Square root of 16 is 4. Take the 4 out. But if that's not clear to you, break it all the way down into its primes, and then just look for pairs. And whenever you have a pair, it's going to break jail and come out. Let's try another one. How about the square root of 1,000? Let's even put a 3 out front here. 3 times the square root of 1,000. You might recognize that 1,000, right away you might recognize, hey, wait a minute, 1,000 is 100 times 10. You might notice that right away. And you might also notice that 100 is a perfect square. 100 is just 10 times 10. But maybe you didn't notice that, and maybe you just kept breaking it down. 2, 5, 2, 5, 2, 5. So no matter how you got to the answer, you could have written 3 times the square root of 100 times 10. And what's the square root of 100?
10.
It's just 10. So this equals 3 times 10. And what stayed in?
The 10.
A 10 still stayed in. That's 30 square roots of 10. Or maybe you didn't recognize that and you wrote this. You wrote all these. 3 times the square root of 2 squared times 5 squared times 2 times 5. See how I broke up my 2 squared, my 5 squared? Because what's going to happen to this? Cancel, cancel, and I'm going to have what staying inside? A 10, right, which is 10. So the 3 and the 2 and the 5 come out, and the 2 and the 5 stay in, and these multiply out to 30. 30 root 10. Either way, you're going to get the same answer. Now, here's what you should do to check. Punch this into your calculator, just like that. Punch that into your calculator, just like that, and you should get the same decimal approximation. So you can check that as well to make sure it's true. Let's look at one last example this time. So we've got -4 square root of 490. So let's break up 490. 490 is going to be 10 and 49. Oh, that wasn't too hard, because I can see right away that 49 is what? A perfect square. It's 7 times 7. Now 10 is 2 times 5. And so we're going to rewrite this as -4 square root of 7 times 7 times 2 times 5. Now this is the trick I always like to use when I teach kids how to do this. Circle any doubles you have, because those are going to break jail. So -4 times 7, the 7 is going to come out, but only 1, because 7 squared, the square root of 7 squared is just 7. These cancel, but then what stays inside?
The 25.
Not 25.
I mean the 10.
2 times 5, which is 10. Now what's -4 times 7?
Negative 28.
-28 root 10. Punch that into your calculator and punch this in your calculator, and you'll see that they're the exact same decimal.
So